Welcome to this lesson on one of the more tertiary topics that you can encounter on the GMAT Quantitative section, three-dimensional geometry. So there are only a few definitions that you'll need to know for three-dimensional geometry on this exam. First is that a single dimension is called an edge, not a side, in three-dimensional geometry, because that's a single line. A side, however, is actually a two-dimensional shape enclosing the figure, whatever the three-dimensional figure is that you're dealing with, and that side is always going to be measured in units squared. And your surface area of the figure is defined as the sum of the areas of each of the sides of the figure. So all of those two-dimensional sides, you add them up, that's how you get your surface area. And volume is going to be the three-dimensional space inside of the figure measured in units cubed. So that's the space that you can put something in three-dimensional. Now, one of the tactics that we talked about in another lesson is that sometimes you have to draw. So here we're going to briefly, and I know I use some tools that make it look a little bit easier than it really will be on the exam, but we're going to talk about how just to draw a three-dimensional figure broadly. So first, try to avoid drawing, because we talked about how if you don't have real numbers, if you have a relatively simple figure, you may not need to draw. But if you're going to draw, don't be a perfectionist, just get it to be good enough. And do make sure that you draw at a reasonable scale. So first step for drawing a three-dimensional figure is going to be to draw two sides that are reasonably offset like this. So you can see a couple of rectangles, just kind of have them diagonally away from each other. Then you're going to connect the remaining visible edges, so you could see these edges, with solid lines. Hey, now we're looking at a three-dimensional box. And then lastly, connect any hidden edges with a dotted line. And you can see that in the back there. That's the edge that theoretically we couldn't see if this were actually a three-dimensional figure. Now, again, you can tell that we didn't dot the edge in the back bottom of the box, but that's okay. It just has to be good enough to represent, to scale, whatever it is the problem is asking about. So then let's just define a rectangular solid such as what we just saw. So first, you're always going to have 12 total edges intersecting at 90-degree right angles at 8 vertices. So you're going to have 8 corners for every box. You're going to have 6 total sides arranged in 3 parallel pairs. So every opposing side is parallel. And your surface area formula is going to be 2 times the length times the width, plus the length times the height, plus the width times the height. Because you're basically just taking each of those sides that you are solving for, just the standard rectangular formula area, and you're just taking 2 of them because we know every side is parallel to another. And then the volume is just going to be your length times your width times your height. So then we get to our special rectangular solid, which is known as a cube. And a cube is going to have 12 congruent edges. So that means 4 edges on top, 4 edges on the bottom, and then you have 4 basically vertical heights connecting those 2 squares, and each of them is equal to each other. So, and of course, they're still intersecting at 90-degree right angles at 8 vertices. You're going to have those 6 sides all the same because they're all made out of squares, again in 3 parallel pairs. Your surface area here, though, can be simplified. It's just going to be 6 because you've got 6 sides, 4 for the walls, a top and a bottom, times whatever an edge squared is. So again, remember that the exam likes you to keep in mind these simplifications. Rather than trying to do the long form surface area we just saw above, you could just do 6 edge squared for a cube surface area. And the volume of a cube is, of course, just edge cubed, hence the term. Because edge times edge times edge is going to be just how you solve for that volume. And that's why anything to the third power is cubed. And if your edge is equal to exactly 6, your surface area units is going to be equal to the volume units, because your volume will be 6 times 6 times 6, and your surface area will also be 6 times 6 times 6. So this is a kind of shortcut that probably not going to encounter on the exam, but if you memorize it and it shows up, it's a really nice thing to recognize. So now let's talk about what sometimes is known as the super Pythagorean theorem. So here we've got our box, right? So we've got our length, our width, and our height, and we know that the longest diagonal squared is equal to the length squared plus the width squared plus the height squared. And you can see how this looks like the Pythagorean theorem extended. So let's talk about how we get there and how to use this formula. So first, it's going to solve for the longest possible line inside any rectangular solid. And the endpoints, as illustrated by the orange line there, are placed in opposing corners of the box. Now, to get to that longest diagonal squared being equal to length squared plus width squared plus height squared, we're basically just doing two steps with the Pythagorean theorem. So you first take your length squared plus your width squared, and that gives you your diagonal squared. That's just your diagonal going from the base corners of the box, right? So that's square. Then, once we have that diagonal squared, we can apply that plus the height squared. You can see a little orange dotted line go up, and that's how we get that other right triangle, because everything is 90-degree angles in a box. We can simplify this to what we started with, which is just that the longest diagonal squared is equal to the length squared plus the width squared plus the height squared. So then our other three-dimensional figures are going to be based off of circles. First is going to be a cylinder. So cylinders are going to be assumed to be right circular unless otherwise indicated on the GMAT. So what that means is that your wall is going to intersect the circular ends at a 90-degree right angle. And when you have an open cylinder, that means you're looking at the wall only. So you can see this kind of illustrated here in this figure. The two tops are empty, and then you basically have your wall. And the only thing you can solve for an open cylinder is going to be its surface area, because you take the circumference, 2 pi r, and multiply by the height. And if you were to cut that cylinder just with one line, you'd create a rectangle. So again, this is something that can come up on the exam, that you can split a cylinder just at any point, and you've got a rectangle of just the circumference as the length times the height is going to be your area. So it's the same just kind of concept without completing the circle for the cylinder. Now, a closed cylinder is going to have the tops covered. And, once the tops are covered, then you can find your surface area, which is 2 pi r times the height, which is still your wall, plus 2 times pi r squared, which is your caps, the endpoints. And we've illustrated that with just kind of coloring them in. And once you've got your closed cylinder, at least on one side, you can figure out your volume. So that's going to be pi r squared, which is the area of the circle, that is the base of one end, times the height, which gives you your third dimension. Now, the other circular figure that you might encounter is a sphere. And honestly, in many cases with both cylinders and spheres, they'll actually give you the formula in the problem just because they are a little bit more obscure, and the test doesn't, and the GMAT doesn't test them as frequently. But if, in case they don't give you these formulas, you know that a sphere is just a three-dimensional circle, and there are two values that you could solve for a sphere as well. First is going to be surface area, so that's 4 pi r squared, because you've got your circumference one way times your circumference the other way. So 2 pi r squared gives you 4 pi r squared. So then we've got our volume, which is just going to be 4/3 pi r cubed. Don't need to go into the proof of this one. Just know that that's the value. And in fact, again, they'll often give you the volume formula if you're encountering a sphere on the exam. So now that we've talked about these basic three-dimensional figures, let's go over to the whiteboard and look at how they can manifest themselves through a problem-solving and data sufficiency example. Okay, so let's take a look at this standard style problem-solving question involving three-dimensional geometry. So as always, we're going to just set up our scratch pad, A, B, C, D, E, put a little line over top, and skip to the end, figure out what we're being asked to solve for. And we see we're being asked for what fraction of the sleeve volume is not occupied by one of the 6 balls. So not occupied volume out of the total volume. And we see our answer choices: 1/4, 1/3, 1/2, 2/3, and 3/4. So if two 6-inch diameter racquetballs, six 2-inch diameter racquetballs, got that backwards. So we've got just a racquetball, and again, it's really quite difficult to kind of do a sphere, so you can do something like that just to indicate it. Wouldn't worry too much about this, but we know that the diameter inside of these is going to be 2. Are able to fit inside a cylindrical plastic sleeve so that each of the 6 balls is tangent to the sides of the cylinder at 2 points, and also tangent to either another ball or the top or bottom of the cylinder at 2 other points. Okay, that's a mouthful, right? So we've got to figure out what that means. So we know that our balls are going to be kind of inside of a cylinder. And again, we're not going to be perfect here, but that's good enough for just putting this together. We know that there's a circle on top. We can kind of dash off the back here, and there's a circle on the bottom. And we know that there are 6 balls. So we're just going to go 2, 3, 4, 5. Oops, 5's a little bit big. And 6. So we've got 6 balls in this tube. Now, what fraction of the sleeve volume is not occupied by one of the 6 balls? So we know we're dealing with volume, and so that means we've got to consider the 2 volume formulas that we just discussed. So we know that the sphere volume is equal to 4/3 pi r cubed, and we know that the cylinder volume is equal to pi r squared times my height. So let's always start with the easier of the values, and that's probably going to be our sphere volume. So we know that the ball volume, because if each of the diameters is 2, we know that the radius of a ball is equal to half of that diameter and 1. So the ball volume is just going to be equal to 4/3 pi. So that's for each ball, of course. Now, we know that we're going to have to take that 4/3 pi and multiply it by 6 balls. So that means the all ball volume is going to be equal to 6 divided by 3, which is 2 times 4, which is 8 pi. So we've got part of this. We know how much the occupied volume is, basically. But now we've got to figure out what the total volume is. So we know that the sleeve volume, we have to figure out the height and the radius of the sleeve. So we already know that the sleeve radius is the same. It's 1 because we were told that the balls fit like perfectly and they're tangent to the walls. So that means the sleeve radius is 1. But then we have to consider the sleeve height, because that sleeve height is the thing that's going to allow us to solve for the total sleeve volume. And we have to recognize that our diameters go not only horizontal, but also vertical. So I know that from here to here is 2. 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 And from here to the bottom of the sleeve is 2. So we can solve for the sleeve height by summing all of the diameters of these 6 balls to determine that the sleeve height is 12. So that means that my sleeve volume is going to be pi times that 1 squared times the height, which we just discovered is 12. And so that's going to be equal to my 12 pi. So our sleeve volume, the total volume, is 12 pi. Now, we have to be careful because the occupied volume out of the total is equal to 8 pi out of 12 pi, which if we cancel out our pi's is going to be equal to 2/3. And that's a big old trap that the exam loves to lay, because you could accidentally pick the wrong answer just at this moment and go, ah, man, I had everything right up to that piece, which is why we wrote out what we're being asked to solve for in the first place. But then we know that if that's my occupied volume, the unoccupied volume out of the total is going to be equal to 1/3. And there's our answer, choice B. And you can see there are a lot of steps with three-dimensional geometry. I mean, that question, talking through it together, obviously takes longer than doing it on your own, but you can see there's just a lot to do, and remember that that's where the exam generates its difficulty. Not by necessarily introducing something new, but combining a lot of topics and making you work through all of the steps to solve for it. So then let's take a look at how geometry can manifest itself in a data sufficiency. So here, we're going to work through things algebraically again. So we start with what we know, and this time probably not going to draw because we have no numeric values provided at the outset, and we know that drawing can take a while and you got to try to make it look decent. So we're just going to work through what we're told algebraically to start. So if the height of cylinder M, so we're just going to say MH for cylinder M height, is equal to an edge of cube N. So that's equal to N's edge. So again, just using some simple notation here. Can cylinder M be placed fully inside of cube N? So can M fit inside cube N? And so we're clearly evaluating the volumes because that's how you're going to fit things inside of each other. So what we need is to determine if 2 pi r h, well, mh, because that's how we're indicating the height of M, is less than edge cubed. But because of the information that we were already told, we know that the mh and the e cubed are basically the same, so we just need to determine is pi r squared less than, we already know that 2 pi r squared, 2 pi r is going to be less than e squared is what we're being asked for, because we know that the height of the cylinder and the cube can basically cancel out. So we can simplify that even further, and I'll bring this down in our need here, because we already know that we can basically cancel out this with one of the edges, because the edges are the same as the height. So condition 1 actually simplifies this for us quite nicely. It just says the volume of cylinder M is less than the volume of cube N. Well, that's exactly what we needed, right? We know the whole thing. We know that 2 pi r mh is less than e cubed, and no matter how it's structured, we're going to end up with this cube being able to, or this cylinder being able to fit inside the cube, because we know that the height is less than the is equal to the edge, and the area of the circle therefore has to be less than the area of the square. So if we can fit the circle inside the square, so the circle fits inside the square, and the height is equal to an edge, no matter what, there's no manner in which that we could have our height basically pop out of our cube anymore. So this by itself is sufficient, and we've got our options as A or D. Then condition 2 just tells us that the volume of the cube is 125 centimeters cubed. So E cubed is equal to our 125, but this tells us nothing about the basic circle of the cylinder. So we know nothing about that cylinder. So pi r squared equals basically open-ended. That's not going to be sufficient, and our answer is choice A. So you can see how algebra is really going to be a big piece of any three-dimensional geometry and any geometry really at all on this exam. And you can see how for data sufficiencies, strip it down to the algebra. Even for that problem solving that we saw moments ago, strip it down to the algebra and recognize that this is one of the harder pieces. And if you don't remember one of the formulas that you need, they're quickly going to turn into questions that you'll want to basically try to eliminate, guess, and move on with, because without some of these formulas memorized, it's going to be really hard to work through anything. So go ahead and work on memorizing these formulas for cylinders, spheres, boxes, cubes, and practice on your own with some three-dimensional problems, data sufficiency, and problem solving to get better at this portion of the GMAT.